and I have a couple
Are we
of
missing
announcements
people?
first. Just a few.
Sorry?
Yeah, I know. I didn't move all the tables closer, but we're also missing a few people.
Or is it because they come from another class, or?
No, because this will be the first class of the day.
Okay.
It could just be getting in the garage.
But you signed up, or you said?
All right, so welcome everybody. Let's get started. We probably will have others join us. Pam,
Do you
Scott.
want me to do announcements at the break then, instead?
Well, first thing to be alert to is next week we are not in this room. You will get an email. We're upstairs. There's some kind of big meeting going on, and they are taking over this room. So, if you come here next week, there will be a bunch of strangers here. So come on upstairs. I think, what did I say?
409.
409 is, I will probably be the last to arrive because I'll be here wondering where the hell is Michael?
We'll ask Darcy to put a sign up.
So, a couple of things to talk about as we kind of get into, well, first we have a new participant.
I've been out of town, sorry.
Well, welcome back. I hope you had a good time wherever it was you were. Let's cover a couple of things. Pam raised an issue about, essentially about things that are not visible to us. They're not in the observable universe. So let's talk about what that's about. I covered it a little bit last week, I think, but it's worth going over it again. So the current model for the early days of the universe is Big Bang. Nobody can explain what happened there. But immediately after the event, whatever it was, in all directions the universe got bigger, got dramatically bigger, and we're talking about in a tiniest fraction of a second, billions and billions of a second. The universe sprung from a tiny atom of something and became enormous almost instantaneously. That outward going shell, so you can imagine if you were present when this happened, the universe would expand in all directions around you. That would be your observation. That outward going shell is still advancing away from us, but it's also getting a boost from the fact that the space between us and that shell is also expanding. So we have to resort to the balloon, ants on a balloon analogy. So if you were an ant on a balloon, tiny little invisibly small balloon gets bigger, and as it's getting bigger, if you drew a circle around yourself, as the sphere of the balloon, the space that it's occupying gets bigger, that circle that you drew is going to get bigger too. And the most distant objects from you, let's say when the universe started out, you're an ant on one side of the balloon, there's another ant on the other side, that other observer is going away from you as fast as the balloon is expanding. And because the expansion rate, the initial expansion rate was extremely high, and it gets an extra boost from the fact that we've had 13.5 billion years of additional time for expansion, that anything that has formed out at that most distant location is now going away from us faster than the speed of light. It's no longer accessible. We will never see light from that shell that's expanding away from us. And remember, every observer has the same experience. We all think everything's expanding away from us. We must be special. We're at the center. Not true. In fact, each of us has a different universe that we observe because we're not in the same place. Pam, did that help? Okay. Now, Bob also, yes, sir.
I have a question. Our time system is based upon a rotation of the Earth around the sun, and we divide it up into days, hours, minutes, seconds. At the time of the Big Bang, what does 1 second mean, or a millisecond, or a microsecond?
Right.
Does that really have any meaning?
Well, it depends on how you want to define time. If you want to define time as how far light travels. So you make a measurement of distance and say, how long, now that's time, how long did it take the light to travel from here to here?
Right?
For us, for example, if you're going to drive to Boulder, we can do that calculation. We can say, well, we know how many miles it is to Boulder, and we'll go make the trip and measure the time it took, and we do a little arithmetic and we get speed. Or alternatively, we have a speed and we can calculate the time it took. Here's the problem. In the early universe, the expansion rate was so high that in a practical sense, you could not do that measurement. Because if you said, I'm here and I'm going to take a trip at constant velocity, maybe using a light, pulse of light, and I'm going to bounce it off of some atom over here, and a friend of mine is going to record when he gets the signal. While the light is traveling, the universe is expanding. So if we do distance and velocity and try to compute time, it's ambiguous because everything is moving away from everything else so rapidly that the definition of time, that definition of time, doesn't give you a consistent answer. So this is one of these, first of all, time is a difficult concept. It's one of those things we all understand unless we have to explain it. Then it becomes a problem. The early universe was so dynamic that talking about distance and time is, both of those are problematic because everything was changing on an extremely rapid basis. Yes, sir.
Trying to get a hold of this concept here. Say this part of the universe was moving away at the speed of light. This part of the universe is moving away at the speed of light. That would give it a rate of 2 times the speed of light. This part of the universe could never see this part of the universe, could it?
Right. Well, first of all, when we talk about these things like the expansion of the universe, we cannot use the standard techniques used by drivers, automobile driver, for example. If you're traveling on the road 20 miles an hour this way, and another car is coming at us 20 miles an hour in the other direction, the relative velocity of the 2 cars is 40 miles an hour. We're all familiar with that. It doesn't work that way at these high velocities. Relativity steps in. And there's one basic principle that changes how we do addition of velocities, and that is the speed of light is the same for everyone. So if you're in a spaceship and you shoot a ray gun out the front of your spaceship, and you would think, well, now the light is going the speed of light plus the velocity of the spaceship. And now we ask another astronaut to measure the velocity of the beam that he receives. He doesn't measure the velocity of light plus the velocity of our spaceship. He measures the velocity of light. All observers measure the velocity of light. So there's some arithmetic involved. If you're energetic about this, you can find this. It's just algebra. It's high school algebra. And it turns out the velocities don't add. So the fact that objects are going away from us that direction or that direction at near the speed of light, their relative velocity is not twice the speed of light. This is all perplexing stuff. And I've said this before in class, I'll say it again, when the professionals get together to talk about these topics, the conversation ends and they go to the blackboard and they start writing math. Because that's the language that works for this kind of. And as our class progresses over the next few weeks, we are going to get into some topics where the math, if we were all skilled mathematicians, far more than I am, we could do the math. But it turns out we can avoid that by drawing graphs. I'm just going to leave that as a teaser, but we are going to study the behavior of black holes without doing math. Somebody's done the math for us, and we have a graphical tool we can use to work on problems related to what life is like traveling around black holes. So That's to come. Today we're going to get our first real exposure to the concept of gravity and Einstein's revolutionary idea replacing or augmenting what Newton did in the 1600s. Newton described gravity with a simple equation. Many of you saw that in high school if you took physics. And that equation stands today. It's the foundation for travel in the solar system. When NASA designs space missions, they use Newton's theory of gravity. Einstein's theory of gravity goes beyond describing what's going on. It explains why gravity has this behavior. And Einstein's insight, which took roughly 10 years to fully develop and turn into a mathematical description, is that the presence of energy in the universe changes what we call space-time. Not space-time, two words. It's now commonly two words together to form a single entity called space-time. And space-time is a flexible structure. I'll just show it to you in a second. It's flexible, and its behavior can be changed. Its behavior is changed by energy. And energy comes in many forms. You all have seen repeatedly E equals mc squared. So that says that energy and mass, where the m in that equation is mass. Mass in the universe changes the shape of space-time and gives us the experience of gravity. That's why this title says there, does it say that? Oh, I guess it's the title of the file. I should have put the title here. It says there's no such thing as gravity. What's happening is energy in different places in the universe distorts space-time, and that alters what happens to objects and light traveling in the universe. And if you go through, as Einstein did, if you go through his very elaborate calculations, you can derive Newton's law of gravity. But Newton was describing it, not explaining it. So I use an analogy I used in the first class. You can go into the forest and look at birds, and you can write down everything you observe about birds, their colors and how they eat, and how they nest and all that stuff. And that's a good thing to do, but doesn't explain why they behave that way. You have a description, but not an explanation. Einstein has given us an explanation for our experience of gravity. So let's get into this. We have covered questions from prior, except Katrina had a very interesting question, which has now become a couple of slides in this presentation, so we'll get to that. Last time we talked about the cosmic microwave background, so if you click on this link, there's a very nice 10-minute discussion that complements what I told you last time. So that's there for your what's available. So the first thing we'll talk about here, to sort of work our way into Einstein's theory of gravity, is special relativity. This is the behavior, and it gets to what you were talking about. It gets to special relativity is about imagining an empty space with observers, but there's no mass in the universe, this imaginary universe. And there's one rule, or sorry, two rules in this special case. The laws of physics are the same for everybody, regardless of how fast you're going or which direction you're going, and the speed of light is constant. All observers observe the same speed of light. So the laws of nature are the same, the speed of light is the same. And everything that happens because of these two rules. And this is Einstein's theory from 1905. Okay, so first thing is material objects cannot go through space faster than the speed of light. So the speed of light is the same for all observers, and nothing can move through space faster than the speed of light. But these two rules I mentioned produce some surprising result. It says that time advances differently for different observers, depending on their relative velocity. So often when you see, if you look at explanations of this, you'll see a train station and an observer standing on the platform on the train, and a train going by, and the observer can see through the windows of the train, he can look into what's going on. He can see clocks and objects in the train as they go by. Now, if the train goes by at 60 miles an hour, it just looks normal. If it goes by at 70% of the speed of light, things start getting weird. So clocks run at different rates depending on your relative velocity. But something is always true. If you're in your space capsule traveling, no matter how fast you're traveling, if you look at your wristwatch, it advances just the way it would be advancing in this room had I worn a watch today. So everyone has an experience of seeing the same speed of light, and time advances for them just like normal. An external observer looking at your watch does not see time advancing 1 second per second. I'll show you an example. And here's an interesting result. What we would consider to be simultaneous events, depending on the relative velocities of travelers, those are not simultaneous when we start talking about speeds near the speed of light. So here, let me show you an example. So here we are. It's not a very good, it's not like a low resolution video, but it shows the key features. Here we are driving down a road. See, the speed limit sign just went by, and there's a building on the right. And we're having the normal experience. And notice we're driving on the left side of the road. These videos were made in Australia. And so nothing exotic going on here, and we're going, say, 60 miles an hour. Now, we're going to go to this frame, and notice this is our fraction of the speed of light. Now, I'm going to try to stop this when we get to look at the speed limit sign, the post, which is, if you were standing next to the pole that holds up the speed limit sign, that pole is straight. But because light is coming to you from different spots on the pole, and you're going at 74% of the speed of light, you end up seeing this curvature. And what's more, as we go down the road toward the building, unfortunately, take a look at this online, and you can get a better experience from it. This is a top view right here, showing you're traveling, and here's that building we were talking about. As we travel, you can see, I know it's a little hard, but those posts, that corner is not straight anymore. It's curved, and in fact, this surface is the hidden surface that you would not expect to see. Because we're going so fast, light has a chance. Let's look at this one. Here's the camera, which represents your eye. Light the objects are traveling so fast that light from a hidden corner can still get to you. And you have the experience of seeing around the corner. Something else happens too. Here we're going, once again, we're going fast. Now notice what's happening to the screen right in front of us. All the light in the universe around us is now being, as we go faster and faster, all that light ends up in a small area right in front of us. So here we're going 95% of the speed of light, and the whole universe is, the whole sphere of available viewing that we have, all of that is right in front of us. This is an interesting problem. Like if we ever develop really high-speed rockets, and you want to go from here to a nearby star, how are you going to steer around the debris that might be in the way? Because everything is condensed right in front of you. These are just a few of the effects that Einstein described in special relativity. We'll go into these in a lot of detail. But there's one more that you should know about. Because clocks really run at different rates, we have something called the twin paradox. So let me get a picture up here. So here's Bob and his sister Alice, his twin. And Alice decides to be adventurous and go on a high-speed tour of the solar system. And she's out there flying at some considerable fraction of the speed of light. Bob, who has not left Earth, he's not undergone any acceleration. He's just sitting on the beach, waves goodbye to his sister. His wristwatch continues to tick forward 1 second, just every second, just like you'd expect. And Alice is in the rocket ship. She has the same experience. But because of special relativity, his clock undergoes what's called maximal aging. He ages the way we're aging right now. She does not. And when she comes back, this is supposed to illustrate, she's returning to visit her brother. She's still young and vivacious, and here he is, looking like me. And this is a real thing. This is proven in the laboratory every day using subatomic particles, and we know if we have one of these subatomic particles, it has a decay time, a half-life of, say, a thousandth of a second, a millisecond. But if we make it fly through the lab at a high rate of speed, suddenly it lasts much longer. It is affected by this result of special relativity. So clocks run at different rates depending on your relative velocity. It's perplexing, but here's an example. We could build a rocket ship and say we're going to go to a nearby star, Vega, which is 25 light years away. So we know that, for example, if we sent a pulse of light out to Vega and somehow managed to get it to bounce off Vega and come back, it would take 50 years to conduct that experiment. 25 years for the light to get out there and 25 years for it to get back. And if we build a spaceship going nearly the speed of light, that from Earth, we would see 50 years of delay between the time the astronaut left and they returned. But the amount of aging, and we're going to say that astronaut's going at almost the speed of light, 0.999 speed of light. You do the arithmetic of special relativity, you find out that the astronaut who made that trip only aged 2 years. It's a strange and wonderful result. The movie Interstellar, some of you may have seen that, focuses on this experience. The astronaut comes back to meet his daughter, and his daughter is in her 80s, and he hasn't aged very much. This is real. So I'm trying to prepare you for the weirdness of general relativity. So we already had some weirdness this morning of special relativity, and now it gets real. So I mentioned gravity is the result, our experience of gravity is the result of matter and energy in the universe changing the shape of space-time. Closer to a gravitational field, like Earth, clocks run slower. There's all sorts of little cartoons you can draw to show this is true. We're not going to try to prove it here. We also know that the equations of general relativity, this is now the theory that includes mass and energy in the universe, that it's something that we now call a black hole can form. We're going to talk about that for the rest of our session today. Rapid changes in the distribution of matter can produce waves in the space-time continuum. We call them gravitational waves. And in the last 3 years, our first successful gravitational wave sensors have gone into operation and have detected big objects moving very fast, producing gravitational waves. And the first detection was of two black holes that merged. So we have two black holes that are orbiting one another close enough that they began to merge into one thing. And for a brief instant, they had the right properties to produce a pulse of gravitational waves. And that was detected at